Let's say a transistor is a resistor whose resistance can be varied by changing its base current. In this video today, we will see how a transistor works and more. Welcome, I'm Reshma and today we will talk about transistors. The main topics will be basic operation of transistor, transistor operating in the cutoff region, saturation region and the active region. A transistor is a three-terminal device with base, collector and emitter. The collector current of a transistor is given as beta into IB, where beta is the gain of the transistor and IB is the base current. The emitter current is a sum total of collector current and base current. Let us consider a small circuit as shown. Let the supply voltage be 10 volts and the internal gain of the transistor beta be 100. Let us assume that the base current is 100 microamps. Using KVL to this voltage path, we can calculate input voltage. Vin is equal to IBRB plus VBE. Here, VBE is 0.7 volt. On solving this equation, we get 1.7 volt as Vin. This means that when 1.7 volt is applied, a base current of 100 microamps is obtained. This can only mean that if base current needs to change, then input voltage needs to change as well. We know that base current is 100 microamps. With beta is equal to 100, we can calculate collector current. IC is equal to beta IB. That gives us 0.01 amps. In the circuit, RC is equal to 100 ohms. Now, voltage drop across this is given as VRC is equal to IC into RC, which gives us 1 volt. On applying KVL to the path from VCC to ground, we can calculate VCE. VCE is equal to VCC minus VRC, which gives us 9 volt. Knowing these values, we can now calculate the collector-emitter resistance of the transistor RCE. RCE is equal to VCE by IC, that is equal to 900 ohms. We can safely say that when the above conditions are present with the base current of 100 microamps, the transistor behaves like a 900 ohm resistor. Let us now increase the base current to 200 microamps. With beta equal to 100, we can calculate the collector current. IC is equal to beta IB, which gives us 0.02 amps. In the circuit, RC is 100 ohms. Now the voltage drop across this is VRC, which is equal to IC into RC. It gives us 2 volt. On applying KVL to the path from VCC to ground, we can calculate VCE. VCE is equal to VCC minus RC, that gives us 8 volt. Knowing these values, we can now calculate the internal resistance of the transistor RCE. RCE is equal to VCE by IC, that gives us 400 ohms. We can safely say that when the above conditions are present with a base current of 200 microamps, the transistor behaves like a 400 ohm resistor. Following conclusions can be drawn from our earlier results. The resistance across the collector and the emitter pins of the transistor can be changed by changing the base current. This resistance is dependent on the gain beta of the transistor. This resistance is dependent on the supply voltage used to bias it. This resistance is also dependent on the resistor RC. By changing the base current, we can change the effective resistance between the collector and emitter pins of the transistor. We can use this variable resistance property of a transistor to build a linear regulator. A transistor operates in 3 regions: cutoff, saturation, and active region. Let us now look at cutoff region. If the input voltage Vn is less than the forward drop of the base emitter voltage drop, then base current is equal to 0. When base current is equal to 0, collector current is also equal to 0 amps. As there is no current flowing, the transistor acts like an open circuit. The resistance across it is very high. Hence, this region is called as the cutoff region. Let us now look at the saturation region. Let the supply voltage be 15 volt and the series resistor be 100 ohms. Let the gain of the transistor be 100 for calculation. Let us assume that IB is equal to 15 microamps. With these known values, we can calculate IC. IC is equal to beta IB, that gives us 1.5 milliamps. Knowing IC, we can calculate VCE. VCE is equal to Vin minus ICR1, that gives us 14.85 volt. Let us now increase IB to 1 milliamps. Then IC is equal to beta IB, which gives us 100 milliamps. Knowing IC, we can calculate VCE. VCE is equal to Vin minus ICR1, which is equal to 5 volt. With these two examples, we can see that as base current is increased, the VCE voltage decreases. This means that the effective resistance between collector and emitter pin reduces. Let us further increase IB to 15 milliamps. Then IC is given as beta IB, which is equal to 150 milliamps. Knowing IC, we can calculate VCE. VCE is equal to Vin minus ICR1, which is equal to 0 volt. Let us further increase IB to 16 milliamps. Then IC is equal to beta IB, which is equal to 160 milliamps. Knowing IC, we can calculate VCE as Vin minus ICR1, which is equal to minus 1 volt. We know that VCC is 15 volt and hence VCE going negative is impossible. The lowest possible value is 0 volt. This means that any collector current higher than 150 milliamps does not have any effect on VCE or IC. This region is called as the saturation region. Let us now look at the active region. This is the region between cutoff and the saturation region. As we saw earlier, cutoff region makes a transistor always turned off. Similarly, saturation region makes a transistor always turned on. In active region, however, change in base current results in change in collector current, thereby changing the collector-emitter resistance of the transistor. This also depends on the input voltage, supply voltage, and other circuit elements as we saw earlier. In this video, we saw how a transistor operates when we change base current. We also looked at its different operating regions. In our subsequent videos, we will see how we can use this to regulate voltage. Till then, keep exploring and learning. Thank you.